will try my best to see this as private and type something back to you in terms of an answer. Also, a couple of things. Again, those recordings can be found on our modules section. I also, I think, updated the grades as well today with your exam scores and everything like that, homework, and the labs that we had. So you can check that out as well in the grades section. Okay, so we'll get started then, and a couple of reminders again that everything here will be recorded. So if you want to see it again, you can, and you can find those in the module section. We will, I think I'm going to open up a little lab sort of meeting afterwards, and we'll talk a little bit about that towards the end of lecture here to answer some questions that you may have in terms of those labs that are still out there. So at this point, we should have 2 labs out there that you need to turn in. One would be the study assignment A, I believe, or maybe it's B. I think study assignment B, which is the Lewis structures. If you have not done that yet, again, you need to online submit that. And then we have the video that was posted last week for part 1 of experiment 7. And again, you'll have to online submit that. Again, that is more of a formal lab. And I think I gave you a couple of weeks or so to do that. Again, you'll submit that through the assignments section on Canvas as well. All right. Any questions on any of that before we get going? Okay, and again, anything that you need in terms of questions, probably type them there in the chat box. And again, please keep the video and your mics kind of muted. Again, just puts up a lot of things on my screen. All right, so we're still here in chapter, I think it's 4, and we're going to talk now about polarity. So we finished talking about hybridization. We finished talking about sigma bonds and pi bonds. Remember that sigma bonds are essentially, you can think of them almost as a single bond. So every first line that you draw, for example, in a Lewis structure are essentially sigma bonds. I guess I should get something right with here. Go with that. So anything that you sort of have there in a, say, a Lewis structure, for example, I think we might have finished with something that looks like this, is a sigma bond. So all these single bonds are the first ones that are drawn, if you will. Those are all going to be sigma bonds. So this guy would have 1, 2, 3, 4 sigma bonds. Now, when we make sort of a double bond or a triple bond, that's where we get pi bonds that occur. And again, pi bonds are a result of a different type of overlap with those orbitals. So when we have our pi bonds, which this right here, for example, might be a pi bond. When we have our pi bond, again, it's a result of those unhybridized p orbitals overlapping side to side. And that's different than a, say, a sigma bond where you have sort of head-on sort of overlap of those orbitals. And in this case, it would have just one pi bond in the example there to the left. So as we finished last time talking about that, again, if you have a sigma bond, a single bond, I'm sorry, basically one line in your Lewis structure, that's considered a sigma bond. If you have a double bond, which if you drew your Lewis structure would have 2 lines, basically that is composed of 1 sigma bond and 1 pi bond. And lastly, if you have that triple bond, which would be 3 lines there in your Lewis structure, it is basically composed of a sigma bond and 2 pi bonds. So both of these pi bonds would be a result of unhybridized p orbitals. Oops, don't want to hit that button there. Come here. So it'd be a result of those unhybridized p orbitals. Again, doing that type of bonding that's happening or overlap that's happening. Any questions on that we sort of finished up with last time? We also talked about the hybridization, kind of went over hybridization again. Remember that you don't have to do all the sort of dots and those lines and stuff like that with the arrows. You could literally just look at your Lewis structure, and really by just looking at it, you're able to determine sort of the hybridization of everything. And it is just about sort of electron pairs. So if we went to this guy, it has 1, 2, 3 electron pairs, and 3 is basically sp2. Remember, s, p, and d. So 3, 1, 2, and 3, sp2. Over here, if we did say the hybridization for this guy, he would have a couple of electron pairs there, and it would have 1, 2, and 3 as well. So the oxygen here would also be sp2. And again, we could even do it for, say, this guy here. It has 1, 2, 3, and 4. So the hybridization of that oxygen would be sp3. Again, 1, 2, 3, and 4. And so again, you can just very much use your Lewis structure to determine the hybridization by counting electron pairs. Again, a reminder as well that if you have a double bond or a triple bond, only counts as 1 when you're doing hybridization or geometry. All right, any questions on the hybridization part that we finished with? Okay, so then we're going to get to the last bit of topic in here, which is polarity. And we've already talked about polarity in the sense of what's known as bond polarity. And bond polarity is basically whether or not a bond between 2 atoms are polar or not. And really what we use to determine that is those electronegativity values that we saw. And if you remember, those values ran from 0 to 4, 4 being the most electronegative, 0 being not so much electronegative. And those differences where you have a difference of 0 to 0.4, that's considered nonpolar. Something above it, so like 0.5 to less than 2, is considered a polar bond. And something usually above 2 is considered a ionic bond. And that's from the difference in electronegativity values. So you would find the 2 atoms basically on that chart that ran from 0 to 4, and basically subtract the 2 numbers. And again, it will give you one of these 2 guys. We oftentimes can represent that with that dipole arrow, where it points to the more negative side, and this side over here that makes sort of a plus sign is the more positive side in a bond. So when we talk about bond polarity, we really use electronegativity, but what we're really talking about now is, oops, go back, try to find something I can write on. There we go, or right on this page. What we're looking at now is what is known as molecular polarity. And again, all this will be on the recording if you need to kind of go back and take a look at it. And when we're talking about molecular polarity, what we're talking about here is the actual molecule as a whole. So as a whole, the molecule. And we're going to start with sort of the simplest ones to determine molecular polarity, and those are our diatomic molecules. And remember, diatomic molecules basically only have 2 atoms involved. So if we look at something like F2, and if we drew F2, like so. When we look at the bond between F and F, if you did look at those electronegativity values, this would have a value of 4, This guy would also have a value 4 since it's the same. So the difference in electronegativity here would be 4 minus 4, which is 0. And that difference in electronegativity tells us that this is a nonpolar bond. Now, because this molecule pretty much only has one bond, and that bond is nonpolar, that means that the molecule itself will be a nonpolar molecule. And in a diatomic molecule, because it pretty much only has one bond, if that bond is nonpolar, like what we have here with F2, it will be a nonpolar molecule as well. Same thing, for example, if we took something like H2 here, they're both hydrogen. So again, when you do that difference in electronegativity, you are going to get a difference of 0. For example, I believe hydrogen is 2.1. So 2.1 minus 2.1 will give you a difference of 0. So again, that tells us this is a nonpolar bond. And because it's a nonpolar bond, and that's the only bond in this entire molecule, the molecule itself will also be a nonpolar molecule. And that's different when we start switching up in terms of a diatomic molecule, that we end up with two different atoms there. So for example, if we got rid of one of those F's and replace it with an F. So if we drew HF, which looks like this, the difference between H and F, again, H being, I believe, 2.1 off the top of my head, fluorine having a value of 4. So when we do that difference in electronegativity for that particular bond, we get 4 minus 2.1, which gives us, that's a lot of math there, I'm going to go with 1.9. And 1.9 is, again, above 0.4, below 2. So this tells us that this bond, based on the electronegativity values here, this bond is a polar bond. And for the exact same reason, because this guy here only contains one bond in the entire molecule, and that one bond is polar, this has to be a polar molecule. So the nice thing about diatomic molecules, when you're trying to decide whether or not the molecule as a whole is polar or nonpolar, is that because it only contains one bond, you can actually use the electronegativity values to determine whether or not that bond is polar or that bond is nonpolar. And if that bond is polar, then the molecule will be polar. And if that bond is nonpolar, then the molecule will be nonpolar. Any questions on that there? Now, if everything was a diatomic, that would be great. It would be super easy to basically figure out, you know, is something polar or non-polar in terms of the molecular polarity. But when we do get to basically 3 or more atoms in a molecule, we essentially have to look at a couple of things to help us determine whether or not this molecule is going to be polar or non-polar. The first thing you have to look at is, are there polar bonds? And again, what we use for that is essentially that electronegativity values. Just like we did up here, basically, to determine whether or not it's a polar bond or if it's a non-polar bond. And if your molecule does have a polar bond, then the second thing you actually have to look at is the molecular geometry. So it's a little bit more complicated when you got 3 or more atoms involved. You do have to look at those two things. Obviously, if the first thing here is no, then most likely the molecule is going to be nonpolar. So if it doesn't contain polar bonds, most likely it will be a nonpolar molecule. But if it does contain polar bonds, it may mean that it's polar, or it may mean that it's nonpolar. So for example, if we look at something like carbon dioxide, and if we draw carbon dioxide here, we can look at carbon dioxide and we could try to determine whether or not this molecule is polar or not. So the first thing that we want to kind of determine is whether or not it does contain polar bonds. So when we look at the bond between carbon and oxygen, we do know that it is polar, and you don't even need those values to determine that. If you look at a periodic table, you'll see carbon and oxygen in the exact same row on the periodic table. Oxygen is further to the right on the periodic table there, which means oxygen should be more electronegative. So in this particular case, we do have polar bonds. We have one heading in this direction, again, pointing to the oxygen that's more electronegative. We would also have polar bond heading in this direction, also pointing to the oxygen, which is more electronegative. Now, this CO2 does have polar bonds. So you may think to yourself, well, perhaps this guy is a polar molecule. But we do have to look at this second part here, which is molecular geometry. And if we look at the molecular geometry of CO2, we have one electron pair and two electron pairs. We also have one bond and two bonds, which means the molecular geometry in this case is linear. And it's basically 180 degrees apart. So basically what we have in this case is this carbon over here basically pulling this way. But because it's in a straight line, basically we have that carbon pulling that way as well. So they're basically equal and opposite of each other. And what's going to happen is, although it does have polar bonds, because of the geometry here, they're essentially going to cancel each other out. And although it does have polar bonds, CO2 is actually a nonpolar molecule. So it's very similar to like two people pulling on opposite sides of the rope, pretty much equal to each other. The rope is pretty much not going to go anywhere, so they will cancel each other out. Any questions on that? So when we talk about these sort of dipole arrows that we draw, these guys are what are sometimes referred to as vectors in basically physics. They have direction, right? And they also have magnitude. And in certain cases, if they head in equal and opposite directions, or if they sort of head right at each other, equal and opposite of each other, they essentially will cancel each other out. But if they head in sort of not equal and opposite directions, they actually will add to each other and become bigger. So let's take a look at something like that. So for example, if we take something like water, and if we take something like water and we draw water, it looks something like this. And the bond between hydrogen and oxygen is also polar. Again, oxygen being more polar than hydrogen. So we would have those guys drawn like that. Let me actually grab an eraser here, kind of make that one a little bit better. Let's fix that there. Let's see if I do a better job here drawing it. There we go. So water here does have polar bonds. And same deal here. When we look at the geometry here, it has 1, 2, 3, 4 electron pairs. And it has 2 bonds. And that means that it is bent or V-shaped in terms of its geometry. And basically what happens in this case is we have this hydrogen oxygen kind of pulling this way. We have this hydrogen oxygen pulling this way. You could kind of envision they kind of meet up here, and they actually will kind of pull upwards on each other. And essentially you can envision, because of the geometry, that water would sort of net move if you kind of pulled from the top. And what ends up happening with something like water is it gets what is referred to, draw big one here, as a dipole moment. And a dipole moment is represented with the same sort of dipole arrows. And basically what this means is the oxygen side of water is more negative. The hydrogen side of water is more positive. And polar molecules, which is what water is because of this, have a dipole moment. So polar molecules will have a dipole moment to indicate that overall, when you take all the bonds into account for a particular molecule, that there is unequal sharing of electrons is occurring. So because of the geometry here in water, we do get a polar molecule. So these are two really good sort of examples. Over here with water, we have polar bonds, and because of the geometry, it will be a polar molecule. While this is a very good example, the CO2 here, that you can have polar bonds, but they can cancel each other out and become something that is non-polar. And just a quick little vector sort of adding how that all works. I'll do my best here with my pen here to draw it. For example, when we do look at water, you essentially have that first one kind of heading in this direction. The second one is going to actually add to it in that direction. And that's why we get the net dipole moment basically heading upwards here, which would be represented by this guy right here, as I totally misdraw that. But you get the idea, I hope. Any questions on that? So in certain cases, those individual bond dipoles will add to each other and create a polar molecule. And in certain cases, they will pretty much cancel each other out. So it's a lot to sort of visualize sometimes in terms of thinking about it in three-dimensional space. So if we, I'm just going to stop sharing for just a second here, just to get something to write on here. Give me 1 second here. Get some fresh paper here, basically. All right, let me come back here. Let me share a little with you. There we go. Let's go back up here, hopefully. All right. Go. Okay, so sometimes we don't want to always try to figure out, by drawing it, is it a polar or non-polar one? So there are certain geometries that are basically what is referred to as symmetrical geometries. And symmetrical geometries are your guys like trigonal, planar, your tetrahedral, your triangular, bipyramidal, your octahedral. And again, here we're talking about molecular geometries. And what all these guys pretty much have in common is when you draw your Lewis structure, you have no lone pairs on the center atom. So you have no lone pairs on that center atom. And if you have this situation and everything attached is the same, it typically will be a non-polar molecule. So these are what are, again, sometimes referred to as those kind of symmetrical geometries that if you have all those guys attached, it essentially will be non-polar. So for example, if we look at This guy does contain polar bonds going from the carbon to the fluorine, as the fluorine is more electronegative. So if we sort of drew our bond dipoles to each of those fluorines, it would have polar bonds. Again, using that electronegativity. But the geometry here is 1, 2, 3, 4. So they're all pretty much equal and opposites of each other. So the molecular geometry is tetrahedral. And basically, these guys are going to cancel each other out. These guys will cancel each other out. So they're equal and opposites of each other. So this is going to be a nonpolar molecule. Now, when you have these sort of symmetrical geometries, if everything on the outside here is the same, and you have one of these geometries up there, it will be most likely a safe bet to write nonpolar molecule. Now, if we switch out one of those fluorines, and again, I'm not drawing the non-bonding electrons here on the outside, and we switch out with something like hydrogen. So for example, carbon and fluorine will still be polar, but what we're missing on this side is that fluorine. So we now have something that's hydrogen. So this is essentially a nonpolar bond, but it's slightly a little bit polar heading towards the hydrogen. So what happens now is you have all three of these guys kind of pulling this way. And this guy is no longer pulling back the other way. He's just kind of going with them. So you could kind of imagine a net movement happening in that direction. And this molecule will go from being nonpolar here, where everything's the same, to, because everything on the outside is not the same, it will now become a polar molecule. Any questions on that there? So symmetrical geometries, draw your Lewis structure, no dots on the center atom. When you draw your Lewis structure, everything bonded on the outside is the same, will usually lead you to a nonpolar molecule. But again, if you change just one of those guys on the outside to something different, it will go from being nonpolar to polar. Now that leaves us another type of geometry. If I can find it. There we go. That leaves us another type of geometry, which is known as unsymmetrical geometry. And when we have unsymmetrical geometries, those are things like your trigonal pyramid. Those are things like your bent or V-shaped. Those are things like your angular, your square pyramid, your just, we don't use that with seesaw, for example. Again, seesaw is sometimes distorted tetrahedral. And there's a couple more that I'm not going to list up here, but we'll go back and take a look at them in just a second. But when you draw your Lewis structures on these guys, these are guys that have lone pairs on the center atom. So these guys, when you draw that center atom, you'll have at least some dots there on the center atom. And if everything attached here is the same, it typically will lead to it being a polar molecule. So that's sort of a quick way you could kind of figure that out. So for example, if we just look at the water example we just did, when we draw our Lewis structure, we see dots on the center atom, and really we see everything on the outside is the same. We know automatically this is going to be a polar molecule. Same thing, for example, if we had NH3, if we draw our Lewis structure, we see dots on the center atom, everybody on the outside is the same, going to be a polar molecule. Any questions on that? Now, really what that leaves you is a couple of sort of things you do have to watch out for. So the first thing is we have linear in terms of the molecular geometry, and that is our 2 electron pairs and 2 bonds linear. And when we talk about linear, because again, it's a straight line, like in CO2, for example, that we saw earlier, because they head in opposite directions, they cancel each other out, so it would be nonpolar. It is possible, again, to have sort of a linear geometry where everybody is heading in the same direction in terms of electronegativity, and that would turn it into a polar molecule. So the traditional linear, which is this one here, the 2 electron pairs and the 2 bonds, you do have to kind of look at it and see, are they heading at each other? Then it'll be nonpolar. Are they heading in opposite directions? It'll also be nonpolar. So again, if you had linear where they're both heading right at each other, also would be nonpolar. So these 2 guys here would be nonpolar. But again, if they're heading in the same direction, it would be polar. And is that linear that I'm talking about there rather than, let me find it here. Let's see here. Where's that little guy right there? I'll take a look at this one. I think it should be on here. And that linear that we were just talking about, again, is different than the expanded octet linear, which is a little bit different. And when we look at the expanded octet linear, which is down over here, it is this guy right here. This guy will also end up being nonpolar molecule. When you have this linear here, which again is 1, 2, 3, 4, 5 electron pairs and only 2 bonds. And the reason for that is if these guys are the same, they're basically going to head usually in equal and opposite directions of each other, and they will also cancel each other out, while these non-bonding electrons are pretty much like a triangle, so they'll also cancel out as well. So that's one sort of geometry where you can have dots on the center atom. In this case, as you can see, you will have 1, 2, 3 dots on the central atom. But because of the geometry here, and if everything again is the same on the outside, it will also be a nonpolar molecule. So that's one exception to that. The other exception where you can get dots on the central atom and the molecule still be nonpolar is this geometry right here. That's the square planar geometry. And basically, because these guys, if they are all the same, basically makes a square, they're basically going to cancel each other out as they're pulling in equal and opposite directions here of a square. So they'll cancel each other out. So those are sort of 2 exceptions to sort of symmetrical geometries where you can get, and I'll put it back up in just a second here. Give me 1 sec. Where you can get basically dots on the center atom, but end up with a nonpolar molecule. So when we look at our little list that we saw earlier, let's try this again here. There we go. So popping this guy back up. So when we look at our list here, we could add really to our list here a couple of those expanded octets that are exceptions. Again, the linear, which is our expanded octet. And then also our square planar, which is also our expanded octet rule. So even though these guys technically will have those dots on the center atom, if everything on the outside is still the same, it will again be a nonpolar molecule. So these are typically your molecules that will be nonpolar when they have these geometries, and everything on the outside is the same. And again, these two here will be the two that have dots that will be the same. Any questions on that? Okay. All right, so as we were talking about, predicting sort of these geometries is really important in terms of looking at whether or not a molecule will be polar or nonpolar. And when we look at something like these two here, so for example, this is bent or V-shaped. So we can make a prediction here in terms of polarity of this. Again, here, essentially all we need to see is I see dots on the center atom. This guy and this guy is the same. Pretty safe bet to say that this is going to be our polar molecule because of that. Same thing over here. I see dots on our central atom. Everything on the outside is the same. Again, it's not square planar and it's not linear in terms of expanded octet. So also we would expect this guy to be a polar molecule. And that's sort of a quick way that you could kind of go through molecular polarity by using your Lewis structure and seeing whether or not there are dots on that central atom. Any questions on that? Okay. So here again is our HF, and that's basically how you would calculate the dipole moment. Not really important for us, but here we do see this sort of electron distribution in the molecule. Because this HF, as we talked about, is polar, more electrons should be over here on the right-hand side versus the left-hand side. So the blue represents kind of cool, if you will. The red part represents sort of hot. There's a lot of electrons in this area of the bond. So here's our NH3, as we also talked about. Again, our polar bonds heading towards nitrogen. Again, we see dots on the central atom. All three of these guys are the same. So we would expect it to have a dipole moment and be polar like we see. Same thing here with our NF3. We have polar bonds between the nitrogen and the fluorine. Again, really, when you draw the Lewis structure, if you see the dots on the central atom and everything's the same here, we would expect it to be a polar molecule, has a dipole moment. You can also see, depending on the shape and what things are there, the dipole moment may be larger or smaller. We're not going to calculate dipole moments in this class, but they can be different in terms of overall dipole moment. So a lot of these we sort of talked about, so let's just take a look at them there just to finish this up here. So our water, as we talked about, have those polar bonds. Again, all you pretty much need to look at is I see dots on the central atom. Everybody's the same. It is going to be a polar molecule. Here, this is our linear geometry, and we do have polar bonds like we talked about. But again, because this is symmetrical, they are going to cancel each other out, and this will end up being a nonpolar molecule, even though it does have polar bonds. This was our SO2 that we saw in the previous slide. Again, just looking at the Lewis structure, dots, same guys on the outside, going to be polar. And lastly here, if we look at CH4, again, the carbon-hydrogen bond is essentially nonpolar. But really all you have to do to look at this is we have all the same atoms on the outside. This is 4 electron pairs and 4 bonds, which is tetrahedral, which is that symmetrical geometry. So basically here, I do not see dots on the center atom. Everything's the same on the outside, going to be a nonpolar molecule because it is symmetrical. Any questions on to kind of quickly determine molecular polarity? Again, molecular polarity is the entire molecule as a whole, taking all the bonds into account. While we talk about bond polarity is just the individual bond between 2 atoms, whether or not that is polar or nonpolar, using the electronegativity values. Any questions on any of that? Here's a few more examples here before we finish. We look at BF3. Our BF3, if we did draw our BF3, again, it would be basically boron in the middle or fluorine This is one of those incomplete octets. So our incomplete octet basically here has 1, 2, 3 electron pairs and 3 bonds. And that's going to give us our trigonal planar geometry. And again, really here, no dots on the central atom. As you can see much better here, it is basically a nice little triangle where each of the corners are basically pulling at each other equally, and they're going to cancel each other out. So this would be a nonpolar molecule in this case. As you can kind of see from the little electron density over here, pretty well evenly distributed, sort of the red spots kind of equal and opposite of each other, which means those electrons are basically being shared equally as a whole in this particular molecule. Any questions on that one? And I think we might have one more here. So last one I think is our CH2Cl2. So when we look at something like this, here we have our H, and it was, I believe, F, if I'm not mistaken. Cl2. So Cl and RCl. So between carbon and chlorine, the chlorine is more electronegative. And again, between carbon and hydrogen is essentially nonpolar, but there's a little bit of pull going this way. So when we look at the geometry here, this is our tetrahedral geometry, which is a symmetrical geometry. But the difference here, though, is when we look at what is attached on the outside, we have some different guys attached. And because of that, this molecule should be polar in this case. And it will be polar because essentially what we got going is we have the chlorines pulling this way, and really the hydrogens are kind of helping pull that way. And we'll get a net dipole moment happening over here where the chlorines are, more positive happening down there where the hydrogens are. And this guy would be a polar molecule in this case. So the quick way that you could do that, yeah, so there's a question about, are you expected to memorize the charts you wrote out for us about bonds, electron? Yeah, so seems a long time ago when we wrote that on the board, but when we did go through the geometry, both you are expected to know if you have to draw a Lewis structure, what the electron pair geometry would be, what the molecular geometry would be, and then obviously now we're talking about polarity, being able to identify the polarity of it as well as it being polar or non-polar molecule. So you are expected to know that chart that we did on, I think we ended up using both sides of the board that time. You are expected to know those things. So essentially in terms of that, you know, you are expected to know what is referred to sometimes as electron pair geometry. And you're also expected to know, obviously, the molecular geometry, which again is sometimes just referred to as the shape. And then with that, obviously, knowing how to draw properly the Lewis structure for these guys. Knowing how to identify the hybridization. Also, how many sigma and pi bonds there are. Know about electronegativity and from this chapter and bond polarity. Again, the individual bond polarity between just two atoms. And lastly, what we're talking about here, which is the molecular polarity. So in terms of all of that, which I think encompasses if I'm not mistaken, chapter, I want to say 3 and 4, if I'm not mistaken. You do need to know pretty much all those things from chapter 3 and 4. And you could probably imagine the question pretty much will be all those things asked of you. Draw the Lewis structure, give the electron pair geometry, molecular geometry, hybridization, and is it sort of polar or non-polar? ID means be able to identify the hybridization of, say, an atom. So that's what it means, like the ID. So for example, if we looked at this carbon here, it has 1, 2, 3, 4 electron pairs, which means it would be sp3. Yeah. So kind of like what we were talking about at the very beginning today and what we talked about last time as well. And again, in terms of the hybridization, that's pretty much what the questions will be. You just have to be able to identify them as sp, sp2, sp3, sp3d, sp3d2. You really won't be asked, like I kind of drew in class and up here, kind of the arrows and all that and how the bonds are made. You just need to be able to identify the hybridization of the center atom and any outside atom as well. So I think, if I'm not mistaken, that might be it in terms of this chapter in bonding. Seems like we've been walking through bonding for several weeks now. Any questions on any aspect of bonding or anything like that? You now should definitely be able to complete your study assignment B, which is the molecular polarity, and be able to turn that in as well. Any questions on that before we head to the next chapter? Okay, we're going to head to the next chapter here. I'm going to just stop sharing for 1 sec to grab the next chapter. That's okay. I'll answer your question in just a sec. Let me just put something up to answer your question about the study assignment and kind of what they were asking. Just give me 1 sec to grab something here. Let's go here, I think. Okay, so let me just slap. Actually, we'll do it on this slide. Why not? Okay, oops. I'll just start one more time here. There we go. I think you should be able to see it, I hope. No? Yeah. Okay. So the question was on the study assignment, there's a column for there's a column for type of bond, and there's a column for polarity. And I'm just going off the top of my head here, but I believe those were kind of the last 2 columns there on it. So that was these last 2 columns that you have. I believe this was molecular polarity. And what they really want in that very last column, if I'm remembering correctly, is what we were just talking about at the very end there. Whether or not, as a whole, taking into account all the bonds that you have in that particular molecule, is the molecule basically polar or non-polar? Yeah. And really what they're asking for in that second to last one, which I think is the type of bond, I think is what you asked there, is they're really asking whether or not that bond is a polar bond. Does it contain polar bonds? Does it contain non-polar bonds? Is it ionic? I honestly don't think you have any that are ionic, but ionic could be an option there. But I personally don't recall you actually having any that's ionic. So really what they wanted you to do in that column, for example, let's take a look at that CO2 that we just looked at. So for example, if we looked at CO2 like we saw earlier, it does contain polar bonds. So really in the column that says sort of type, really what it's looking for is, is that a polar bond? And there's a polar bond. And you can show that either one of two ways. If you want on your Lewis structure, you could draw the arrows, or you could simply, you know, kind of do it like that. That's really what I think they were looking for in the one that says type. And then in that last column where it says molecular polarity, really what they're looking for is, as we talked about, although it does have polar bonds, this is really overall a nonpolar molecule. So if I remember from the top of my head, that's sort of what they're looking for in that particular case. If you had something like the CH4, really the carbon hydrogen bond, if you use a difference in electronegativity, is like 0.4. And that means that is going to be pretty much nonpolar bonds. And this would also be a nonpolar molecule. Yeah, so that's really what that column is looking for. Yeah, the last column is exactly, the very last column is exactly what we were just talking about right before we ended. The actual overall molecule, taking every bond that you got into account, that's what it's looking for. It's really like one answer. Is it polar or non-polar? And that means the molecular polarity for that very last column. And that second to last column is really what they intended, was something like this. So for me, if you want, you can, if you want for the one that says type, you could write, if you want, you could write your polar or non-polar bonds. And if you want, you could show the arrows on your Lewis structure. Or if you don't want to show the arrows on your Lewis structure, you could write polar bond, kind of like what I did here, and kind of show the arrow that way as well. So you could do it one of two ways. Other questions on that? All right, then let us continue on to the next chapter here. We'll switch up the color. So we're going to go to chapter 5. So chapter 5, all that Lewis structures and that drawing, we're actually going to get into atomic mass, moles, doing those type of conversions, calculating empirical and molecular formulas as well. So we're going to start with atomic masses. So one of the fundamental properties of an atom is its mass. And again, a reminder that all these lecture notes, if you want to kind of print them out like normal, are on our Canvas site in the module section. Again, if you go back and watch the recordings, you'll be able to see everything that I put on the screen and all that kind of stuff. So it is related to, obviously, the mass, the number of protons, electrons, and neutrons that there are in a particular atom. But obviously it's extremely small, so you can't just kind of pick it up and put it on a balance or anything like that to weigh it. So when we have something like that, what typically occurs is that we assign something as a standard, basically, to compare everybody to. And basically in chemistry, what they chose as the standard for atomic mass is an isotope of carbon, which is the carbon-12 isotope. So again, carbon-12 means that the mass number is 12. Again, the atomic number, which is what you can find on the periodic table, that is 6. And again, what that means, if you remember from the earlier chapters, this guy's got 6 protons. 12 times 6 is 6 neutrons in this case. And it has a mass of exactly 12 AMU. So 12 AMU is atomic mass unit. And that technically is, when you look at the periodic table and you look underneath somebody, for example, like carbon, it is the number that we see on the bottom there. It's that 12.01. And that is basically the atomic mass in AMU. And in AMU, what that means is one atom of carbon has a mass of 12.01 AMU. So they basically use this carbon-12 as a standard to compare everybody else to. They basically would go, hey, hydrogen is only 8% as big as the carbon-12 isotope. And they would do a quick calculation and go, hey, like 8%, as we'll see on the next page, I think, is about 1.008, which again, if you look on the periodic table under hydrogen, that is typically, what you would see there. And they did similar types of calculations pretty much for all the elements that you see on the periodic table. As you can see, there's that calculation. And we do get something like 1.008, 5585 in terms of iron for its atomic mass. And usually when we talk about atomic mass or go to the periodic table to basically use the atomic mass, in terms of significant figures, usually it's 4 sig figs is usually how many numbers that we kind of pull off the periodic table when we use it. Again, depending on your periodic table, you may see a wide variety of numbers, a lot of numbers, not very many numbers, but sort of the standard rule when you pull a number off there is the 4 significant figures. So that's again why a lot of times for hydrogen, we will round to 1.008. Again, that means AMU in an atom. And although when we're done with this, we probably won't use AMU very much, and we'll see it a little bit later on this chapter. Usually what we use in terms of units off the periodic table is not usually AMU, but it is usually, as we will see, grams per mole. And essentially, they are the exact same thing when you do some of those conversions. So when we do look, though, at the periodic table and we look at carbon, for example, what we do see is that number that I wrote up earlier, which is 12.01. And you may say to yourself, well, if they use carbon for the standard and that standard had exactly mass of 12, why when I look at carbon is the mass basically 12.01? And that's because basically what we see on the periodic table is what's referred to as the average atomic mass, although most people don't call it that. And it's basically the average atomic mass of all the naturally occurring isotopes for a particular element. So for example, when we look at carbon, there's the carbon-12 isotope and there's the carbon-13 isotope. And each of these occur at a sort of a different percentage, kind of naturally. And this is what is sometimes referred to as percent abundance or relative percent abundance. And for example, to calculate the atomic mass of a particular element, what you essentially do is you take the percentage of the first isotope and then you times it by the atomic mass of that first isotope. And then what you do is you add it to the percentage of the second isotope times the atomic mass of the second isotope. And then essentially, if you have more, 3 isotopes, 4, you just continue that process. Obviously, when we calculate the total percentage of each of these guys, it should really equal 100%. Then we know we essentially have all the naturally occurring isotopes. So for example, if we follow this formula here, which I think might be on the next slide, so let's take a look at that. So if we take our carbon, and what we see here is carbon-12, which has a mass of 12.00 AMU. Occurs about 98.89% of the time, while carbon-13 occurs about 1.11% of the time. And if you add up these two percentages, it equals 100% of all the naturally occurring isotopes. So here's the mass of the carbon-13. So basically to calculate it is what we were just talking about. This right here is 98.89% converted into a decimal. So you could either divide it by 100 or just move the decimal 2 places to the left, times the atomic mass of the first isotope, which is 12. And then the key here is adding. People always want to multiply here, but you're going to add. And then this is basically 1%, which was moved 2 places to the left, times the mass of our second isotope. And when we do that, that is how we get that 12.01 number that we see on the periodic table when we look underneath carbon. And again, it really is the average atomic mass of all those naturally occurring isotopes. Again, like I said, most people don't really call it the average atomic mass. They just kind of call it the atomic mass. Any questions on that, or how to calculate the average atomic mass? And it is important to remember, like it kind of says up there, if you were able to sort of grab some carbon atoms, you would never really find one that has a mass of 12.01. You would either find a carbon 12 atom, which has a mass of 12, or you would find a carbon 13 atom that has a mass of about 13. You'll never really find one that's 12.01. It's just really the average atomic mass for that particular element. So atoms have very tiny masses. In case you're curious what the relationship is between an AMU and a gram, it's right here. 1 AMU is equal to 1.66 times 10 to the minus 24 grams. Essentially what that's going to do, as how we're mostly use the atomic mass off the periodic table, is essentially mean that when we calculate something like grams per mole, it's going to be numerically equal to the number that we see on the periodic table. All right. And I'm just going to skip through these. We're not going to worry too much about them, but they're basically just very simple sort of conversions here. If we want to know the atomic mass of 75 atoms, for example, here of aluminum, this would be found from the periodic table. And again, one way that you could use that number from the periodic table is how many AMUs there are in an atom of that particular guy. So again, if you looked at aluminum, it would be 26.98 AMU in an atom. And that's how you would use it at conversion factor. Here again, the atoms would cancel, and that would leave you with AMU that's left over. And it would tell you that, if I grab my calculator there it is, 2024 in terms of the AMU. Any questions on that calculation? Again, very similar to what we'll talk about in just a second. All right. So one way that we could kind of determine the mass of each of these isotopes and sort of their relative abundance is through a process known as mass spec. And basically in mass spec, what we do is we kind of send a sample through a machine where it pretty much gets heated up and kind of broken apart into its atoms. And basically they will be separated out by size. And I think there's a nice little diagram of that. And basically what you'll get when you do that is you'll get this little graph here, for example. And in this graph here for chlorine, we have 2 isotopes of chlorine, chlorine 35 and chlorine 37. And we can see that chlorine 35 is about 75% abundance, while 37 here is 25-ish in terms of abundance. And again, if you sort of calculate that, that's about 100%. And they do come out at sort of different masses. So by using this sort of process of mass spec, that's a way you could kind of get those values that you typically will see, the percentage of one isotope versus another. I think I might even have a better picture here, perhaps. Let's see here. There it is. So this is sort of the process here of mass spec. And again, you pretty much send your sample through, gets obviously kind of heated up, or electrons gets ionized, and it goes through sort of an electrical field component and then also a magnetic field component. And then as it kind of goes through here and bends, the lightest particles will kind of come off first, the heavier guys will come off there, and you'll get a graph very much like what we saw on the previous page. and you'll be able to figure out, again, the percent abundance of each of those isotopes and also the atomic mass of each of those isotopes by using this process. So for example, if we look at a problem like this, if copper is 69.17% copper 63, and it has a mass of 62.9396, and the rest is copper 65 with a mass of 64.9278, and we want to find copper's atomic mass. This is a problem, again, where we can use our formula that we saw earlier, and that formula being that the atomic mass is equal to the percentage of the first isotope times the atomic mass of the first isotope plus the percentage of the second isotope times the atomic mass of the second isotope. And again, you could continue that if you had more than two isotopes. So if we look at what we got here, we have copper 63, that's 69.17%. And it has a mass of 62.9396 AMU. We also have copper 65 that has a mass of 64.9278 AMU. So if we look at what we have for our first isotope, we have both things. We have the percentage. We also have the atomic mass of that first isotope. For our second one, we have the atomic mass, but we do not have the percentage. And we could find the percentage pretty easily, assuming that these are the two naturally occurring isotopes. They again should equal basically the 100%. So since we know that copper 63 is 69.17%, we basically could find the mass of copper 65, if you want, you can call it X, by solving for X. And basically what that means, we need to subtract from 100. And if we do that, and you will end up with, hang on one second here. Sorry about that. Guess I should remember to turn the light on. Huh? Let's see. So 100 minus 69.17 gets us a percentage for copper 65 of 30.83%. So by assuming 100 there, we can basically figure out our missing percentage. So now we do have our missing percentage for our last guy, which is 30.83. Any questions on that calculation so far? So now we do actually have everything that we need to calculate it. So we could say that the atomic mass would equal, we want to convert our percentage into a decimal. So our 69 will become 0.6917 times the atomic mass of our first isotope, 62.9396 AMU. Again, here we're going to add, not multiply, times it by the percentage of our second isotope. That's going to be converted into a decimal, times the mass of our second isotope, which is 64.9278 AMU. And if we do that there, we will end up with $63.55 AMU. And again, if you go to a periodic table and you look on copper there, That is the number that you will typically see underneath there. Again, here we went to 4 sig figs, which is very common for atomic mass or even molecular mass that we'll talk about as well. Any questions on that calculation there? Okay. Let's continue on. What's filling in is exactly what I wrote on the screen there. So the next thing we're going to talk about is a really important sort of calculation and idea in chemistry, and that is what is known as the mole. And the mole is the amount of elementary substances there are in basically 12 grams of the carbon-12 isotope. So in life, we have a lot of things that we use, or words that we use that represent something. So if we say we have a pair of something, that means that you have two. If you say you have a dozen, that means you have 12. So when we say we have 1 mole of something, it does represent a number. It's on the bottom there. That's our 6.022 times 10 to the 23. And the units here could be atoms in certain cases. They could be molecules in other cases. They may be particles, maybe pizzas. It is dinner time, right? Maybe shoes, all that kind of stuff. But obviously in chemistry, atoms and molecules are going to be used a lot. And we represent a mole as that 6.022 times 10 to the 23. That again is what is known as basically Avogadro's number. So that's Avogadro's number. And we essentially will use it as a conversion factor. So Avogadro's number is essentially our conversion factor to convert between two things. It is to convert between when you have moles and you want to go to atoms or molecules, for example. And we also use it the opposite way when you have atoms or molecules and you want to convert to moles. And we're essentially use it as a conversion factor. And by the way, an important thing in terms of sort of the abbreviation there, a mole is actually a mole. So that is the abbreviation for mole. It's actually MOL. Sometimes when people see that, they think molecule. And again, they start doing sort of wrong conversions. So we would use it as sort of a conversion factor where if we had atoms, we would on the bottom use Avogadro's number. And moles would go on top, and that would get us moles. Or vice versa, if we started with moles, we would use Avogadro's number on top. To get atoms or molecules in that case over here, right? If you were doing molecules. So it really is going to be used as a conversion factor to go between those two things, either to go from atoms to molecules, atoms to moles, or go from moles to atoms. And people always want to use Avogadro's number in every calculation they ever do because they're like, I learned that number, I should do it and use it. You should only use Avogadro's number whenever you're asked to convert a number that is already in atoms, molecules, particles, something like that. Or if you're asked to find an answer that needs to be in atoms, molecules, or particles, or some number like that. You should not use Avogadro's number in every calculation. It does need to specifically kind of have those numbers in there. Any questions on that? I think this might be a good stopping place for now. Let's talk about a couple of things before we sort of wrap it up here for today in terms of the lecture part. First off, we will be back on, sorry, I was going to say it's Thursday, not yet. Thursday, again, we'll continue lecturing at our normal time. All these will be posted through a link on our Canvas site if you need to watch them again or watch them for the first time. And again, that could be found in the module section. In terms of the lab scheduled for this week, there are a couple of study assignments. The first one, I think, may be about naming, which obviously we haven't got to because we had a little break from lecturing and all that. And the other study assignment, I think, is about what we're about to talk about here, or getting right into right now, which is like grams, moles, and stuff like that. So those two study assignments, which I think at this point would be study assignment C and D, we will not technically do them this week. We're going to push them off probably till next week. So they won't be due obviously anytime before next week, when we'll actually get into all that stuff. So they will be due sometime down the road. So again, in terms of lab outstanding, what you should have to turn in is at some point the study assignment B, which is our Lewis structures, which at this point after today's lecture, you should definitely be able to answer everything that's on there. Again, you need to take pictures of everything, kind of convert it into a file would be great. Upload it through the assignment section before the due date. I think I actually gave you until next Monday, I think, to do it. So that should be enough time, hopefully. And then the other one was, there was the link to experiment 7 that was up, I believe, last week. Again, if you haven't done so already, you do need to go and watch that video. You do need to fill everything in terms of your lab notebook, like you were doing the experiment. So you should have procedures, observations, tables of data and stuff like that. Again, we only did part 1. So you just obviously need to do the calculations for part 1. That is technically a formal lab report that does need to be typed. So you do need to type it much like what you did with your hydrate experiment. You also need to do the pre and post lab questions for that as well. Now, some of those questions and some of the calculations for the pre and post lab, including actually the lab as well a little bit, we will get into hopefully during lecture on Thursday about empirical formulas and some molecular formulas. So again, that lab report, I think I pushed it to April something, I think, if I'm not mistaken. So you got some time to sort of submit that. You do need to do the carbon pages for the experiment 7 where you watch the video. Again, you want to write everything in your notebook just like you were performing the experiment based on what you saw in the video, what data that was given to you in the video. So I believe, again, he gave you some masses and other sort of observations, like what did the solid look like, as he was doing it, or gas that was produced. So you should have all those kind of observations in your pages with your procedure. And again, you should have a data table, much like the one in the manual part that explains the experiment. And it should be filled in and all that. And again, you need to type it up and do the pre and post lab questions. So again, you should hopefully, I made sort of the due date down the road, give you some time to do that. Also give us some time to catch up on the topics so you'll know how to properly do that. Any questions on that sort of stuff? No, so the question was, do you have to fill in the experiment pages for experiment 7? So technically speaking, since it's technically a formal lab, if you were in class and did it physically, you actually wouldn't fill in those experiment pages. I'm assuming you're talking about the ones in the actual manual after the procedure and all that. You wouldn't fill out those experiment pages. You would actually just fill everything on your carbon pages in your notebook. And that's again what you should do for that experiment when you're watching the video. The only sort of experiment pages that you will fill out is you could use the experiment pages to do the pre-lab questions and the post-lab questions. So like a normal lab for the pre-lab and post-lab questions, you could just work them out right there on those pages. But everything else that you technically would write or fill out for that experiment should be done on your carbon pages like you were still kind of doing the experiment. Other questions on that? It's a good question. So the question about where you will submit assignments, You'll submit assignments. Actually, at this moment, you could go through the assignments section, I think. If not, I'll double check. I got 5 like Canvas sites going at once here, but I'll double check. If not, I'll put a link maybe in the module section. They'll link you right to the place where you could kind of submit your assignment for each of those. Because in the assignments, if you do click on the assignments page, which I think you can do, you'll see everything, including past assignments up there. So, you got to kind of look for the one that you're trying to submit. The question about resubmitting an assignment, I don't know if once you submit it on Canvas, if they'll let you upload anything else. If that, I honestly don't know if you can or not. If you can't, just shoot me an email and tell me what you need me to do, and I maybe could adjust it to let you resubmit it. Okay, but maybe go back and see if they'll let you upload something again. But I just don't know off the top of my head if you can, after you submitted the assignment, kind of resubmit it. You might be able to, as long as the due date hasn't passed, but I'm not 100% sure on that. So if you are sort of in that situation where maybe you submitted too soon, just shoot me an email if you can't resubmit, and I'll try to help you out with that. In terms of the exams, unfortunately, there's really no way to kind of get your exams back at this point. If we maybe come back together in person, you'll be able to kind of look at them. I just don't really have a way to kind of do that, unfortunately. Any other questions on lab? Okay, so in addition, you might have noticed as well, there's a separate meeting for lab tonight. So what I was going to do is, again, since you do have those 2 outstanding sort of assignments, you may have some questions on some of that. What I'm going to do is I'm going to start the lab meeting, and I'll hang out for a little bit. And if you like, you could pop in and ask some questions or something like that through the chat, and I'll try to answer your questions if you do have questions on either, at this point, I would assume study assignment B, or maybe the experiment 7, or you could ask about anything in terms of chemistry that we've been talking about as well. But so I'll hang out there for a little bit. I probably won't hang out the entire 3 hours, just so you know. So if you do have questions, at least maybe I'll be there for at least probably an hour, maybe an hour and a half. We'll see how it goes or how many people are there. So if you do have questions, that's my plan. I'm just going to take a little break first, obviously, and maybe start around 7:15 or so. And it'll be a separate meeting. So if you want to get to me in the lab sort of section to ask a question or something like that, as you're maybe working through some of this stuff, you can kind of join back up. There should be a link again on Canvas to go to the lab meeting. And again, I probably won't be there for the entire 3 hours unless everybody's there for the entire 3 hours, but I'll definitely be there at least for an hour or so if you do have questions or something like that. That's a very good question about exam 2. I'm still working that out. So in terms of material wise and stuff like that, I'll try to have an update for you on that on Thursday for exam 2. If I'm not mistaken, right now is technically scheduled when we come back from spring break, I believe. It will definitely for sure, exam 2 will cover chapters 3, 4, and 5. And we'll kind of see where we're at maybe as we're going through. So because we kind of lost a little bit of time, and we lost some time this week kind of reviewing the class and everything that's going on. We're a little behind, obviously, on the lecturing part. So like I said, that's also why those study assignments that are technically scheduled for this week for lab will also be pushed back and stuff like that. So we'll talk more about when those guys will be due. Other questions or anything like that for right now? Okay, so again, if you do have some questions about some of the lab stuff or calculations or something like that, or the study assignment, again, in about 15 minutes or so, I'll open up the lab link and meeting. And again, you can hop in and ask a question or something like that and get some help if you need. If you're all good on that, then I probably will see you back here on Thursday. And have a good night. And if I don't see you, you're welcome. Have a good night. So I'm going to officially probably end this meeting. Thanks, you guys. Have a good one. I'll see you in lab if you're heading that way. Have a good night.